Yes, so then I just want to remind you now, on the top of the collaborative document, you will find the link to all the episodes that we're going through today. So we just Bjørn just had Why Use a Cluster, and now we're gonna go on working on a remote HPC system. So you'll find the link to the material by clicking here. Yes, and this is the page. I will turn my page into a kind of presentation mode, so it'll look a little bit different than what you see, but it's hopefully to make it a bit easier to follow. So first of all, now at this point, at day one of the HPC course, you should all be in the state where you actually know how to find your terminal. You have a little bit of experience or more experience with Linux. So the prerequisites to follow the rest of the course should now be okay, which is you should have SSH. You should be able to find a terminal on your Mac or your Windows or your Linux system. And also you should have you should have a account and have access to a project, typically the training project. So I know that some of you have not applied for access to a project, and it's probably a bit late to help you with that now. But if you still don't have access and you want to have access, you can contact us, contact Espen on the Zoom chat and see if we can help you there. But we will assume now that you're all set, because we had the login session on Monday and we had the Unix intro yesterday. So we assume we're all good to go for the rest of the class for today and tomorrow. So let's now look at how it is to work on this remote system. And for those of you that were present yesterday and Monday, this is actually a repetition, but just to get you all on board, some of it is a repetition. So since the HPC cluster is not sitting on your desk right now, it's actually remote somewhere out there in Norway, you need to connect to it from your laptop and through the internet or through some network.
Interesting that you mentioned about the desktop, because
Yeah.
the NVIDIA launched yesterday or last week something called DGX Spark, which is a tiny cluster that you can
Oi.
have on your desktop.
Oi.
And I think it was Musk that got the first one or something.
How large is that?
No, it's 1 petaflop
Oi.
that you can have on your desktop.
Okay. Well, okay. So you can have a little cluster on your desktop, but we don't have that now, I'm assuming. Yeah. So we'll use SSH to connect, basically. And so I think that we should then basically do that. So let's try to log into the cluster. And the syntax for this is SSH, which is the secure shell. And it's secure because it uses encryption to connect in the connection, so that nobody can just tap into the connection and just read everything in plain text. It's encrypted and secure. And then it's your username. Mine is Maiken P. Yours will be something else. And the at symbol, and then the HPC system that you're logging into. And in our case, we will use Saga. So you can find your terminal now and try to log in. So I will do the same. SSH Maiken P at sagasigma2.no. And you have to get your phone ready, because it'll ask for two-factor authentication, which you all should have set up by now, hopefully. And then I have to actually manage to log into my phone. Let's see. I'll press enter now. And let's see. And I have a very long password, so yes, it worked. Let's try to check how many people have managed to log in. So if somebody from NRIS could make a little poll for me to check where you can answer if you managed to log in or not on the collaborative document, that would be super. Put an O if you manage to log in. Okay, looks good so far. And for the ones of you that, for example, don't have an account and are not planning to do it to actually follow along and type along, just feel free to just follow. And material is anyway there for you for later when you have your account ready, and then you can try and type along and do the exercises afterwards. Good, looks good. So I think we'll move on. So now we have to try to understand where we actually are. So Björn briefly mentioned, and he showed you some pictures that you see like kind of the servers are, looks like they're chunked into parts. And they are chunked into parts. So it's not like one big machine, it's several machines linked together, as Björn mentioned. And when we log in, let's check where we are. So I think that already you might get an idea that we are on something called login 5, at least I am. So let's type the command hostname, which will show you the name of the machine. And for me, the name of my machine is login-5. And you might have a different number because there are several login machines. So basically,
For Saga, I think it's 5 login machine.
right. So I came on the last one, and you might be on 3 or 2 or whatever. So those are special machines, basically exactly for accessing and ending up there when you SSH into the machine. Yes. So that is a good chance to talk about the different types of nodes. So we use the word nodes typically to mean a machine, a login node, a compute node, and so on, or a worker node. We use them a bit interchangeably. And the login node, that is basically your gateway to the cluster. So there are things we do on the login node and things we definitely should not do on the login node, and vice versa on the compute node. So for the
Mike,
sorry.
if you write who, now you show all the people that are on. So you see that you share the login node with a lot of people.
Very good. Yes. So yes, I am not there alone. We are many people on that node at the same time. And that means that we have to be a bit careful about what we do, because if I run something on this node which occupies all the CPU and RAM on the node, I will be basically blocking the other people. So the login node is basically just for simple things. It's for logging in, it's for copying files, maybe from your laptop to the remote HPC to the login node. It can be used for installing some software. And it's used for submitting and monitoring jobs, but not running jobs. So we'll talk about more what that means soon. On the worker nodes, the compute cluster nodes, those are the ones that do the analysis. So those are the ones that will run your analysis for days or hours or weeks, depending on your type of job. And there you basically scaled for that type of job.
And on those, you can in fact be all alone if you have kind of
Exactly.
specified.
Yeah. So that's the difference here. So you can ask for one or several nodes, and you can use them all yourself if you need that and have asked for that. You can be sharing with others too, but there is a system to make sure that you're not using more than what you asked for. So it's kind of safe to work on those. So that's a difference between the login nodes and the compute nodes. Yeah, and it's also a great place to compile software. Compiling software can take a lot of memory. If you need to compile some software that's kind of takes a lot of effort, that's where you would do it.
And I think on Olivia that's forced kind of in a
Oh,
way.
yeah.
So there you have to use the compute nodes for compiling, whereas on
Yes.
the other systems you can in fact compile.
Yeah. In a perfect system, in a perfect world, everything would be very easy for the user, and the system would not allow you to do things that you shouldn't do. But in the real world, things are a bit more complex, so we have to rely on you all following some guidelines and some best practices that we hopefully will teach you. Yes. Now, to interact with the compute cluster and to submit your jobs and run your jobs, we use something called a scheduling system. And Björn will talk much more about that in the next session. But we're just going to touch briefly upon it now because it also gives us some information about the different nodes that we have in the compute cluster. So all of the interaction with the worker node is handled by a software that we call a scheduler. And there's many types of schedulers. We use Slurm, and it's used by many HPCs across the world. So it's a very common and well-known scheduling system. So if you learn Slurm, you're likely to be able to use that also if you get access to a large like Euro HPC system or some Lumi, some AI factory system. If you have heard about these terms, that's then you know what I'm meaning. Otherwise, it's just basically other HPC centers that are larger and Europe or Europe-centric. There's another one called HD Condor, which is also quite a lot used. I think maybe it's used more in the US. But Slurm is a useful thing to learn. So what I want us to do now is to use one Slurm command, which is sinfo. And typically Slurm commands, they start with an S for Slurm, and then it's something that's understandable after for info. So if I write in sinfo here, I will get quite a lot of output, and it looks a bit messy here. So we can instead use this clipped down version here that we have in the documentation. And information here is about basically the compute nodes that we have in the system. There's something called partition. It's something telling if the node is available or not. There's a time limit which tells you how long jobs are the max that you can have running on the certain compute nodes, the number of nodes, the state they are in, and the list of nodes. So as you can see here, we have kind of divided the compute cluster into partitions. So some nodes have, for example, a lot of memory. You see there's a big mem here. So those are machines with extra large memory. There are some nodes, Optimist, that I think you can kind of get access to quickly. Maybe it's for shorter jobs. Do you know, Björn?
Optimist is the whole cluster
Okay.
But the types of these jobs can be easily killed if jobs with higher priority uh, comes in. So it's a
Right.
kind of job you submit to the Optimist queue if you have a job that you just want to try to get run as long as possible. You see, the time limit is infinite,
Yeah.
for instance. So you then it uses the free resources if they are there.
Mm-hmm. But then if another job with higher priority comes in, it might be killed.
Yes, so it's highly probable that the Optimist job will get killed at some point.
Yeah,
Yes.
so it's a bit more experimental. Or if you have, for example, checkpoints, if you know what that is, you can have like your analysis, which kind of has checkpoints to stop at certain points, and then it can pick up from where it left next.
Yes. I also think you can use if you're running out of compute time that you don't have an
Ah, yeah.
allocation longer, then you also can use Optimist, I think.
Okay.
But
But
I'm
anyway,
not sure there, but I think
yeah,
it's like that.
the documentation will tell you all about. Maybe somebody can link to the documentation in the collaborative document, because that's where you will have explanations of how you can use these different kind of partitions. Yes, and then we have tabs here for other systems. Sorry. Fram is another HPC cluster that's located in Tromsø. Betsy, as Bjørn talked about, it's in Trondheim together with Saga. And then Fox is the local, little smaller HPC system that we have at the University of Oslo. And you see it has kind of similar concepts, but yeah, just different kind of flavors, basically. So yeah, so many typically HPC clusters have like a variety of nodes, and then they're optimized for particular workloads. And one thing that you don't see here is GPU. That will be in Olivia, that will you'll certainly see some GPUs there.
Well, the Excel queue is GPUs.
But
Yeah.
it says, yeah, and yeah, it depends on the naming. So exactly. So it depends on the naming. So in Fox, we've decided to call the nodes that have GPU cards, the graphical cards used for machine learning and for kind of AI type of workloads. We've called them GPU. But on Saga and other, it seems you don't have that naming convention. But the Accel partition indicates that this has GPU access. So that acceleration, basically, it means. Yes, let's say I just have to scroll down to see. Okay, and what's the time? Yeah, we still have time. Good. So what's in the node then? Well, Bjørn actually already said that it's basically the same as your laptop, but it's just probably bigger, better, or at least more than what you have on your laptop.
More cores, more memory. Then
Yeah. So we have the usual components. We have CPUs, processors, of course, different names used for that. This is like one machine, and you have many of those stacked on top of each other. So you can see here, this is like, to the left here is like a rack with 1, 2, 3, 4, 5 slots in this case. And then when you take out one of those, that is one node. That's one machine, independent machine. And then they're linked together with cables, with network cables, so that they can actually behave like one if you ask for that. So that you have the RAM in one machine can be connected and so on with the others. So that's the big benefit with HPC systems, that you can have these links between the nodes. You also have some local storage and RAM, as I said, memory. In addition to local storage, so the local storage, that's local for that single node. that means that if I'm on one other node, the node under here, for example, I will not be able to access the local storage that I have in the other node. But for that, we have something called shared file systems.
Stop a little bit. We have a question that we should repeat the things regarding RAM on the node.
Okay, let's see.
It's in the Zoom
Was
chat.
it in Zoom?
Yeah.
Well, I don't know what you're referring to, but for in an HPC cluster, basically we have nodes that are connected to each other. So that means that the memory can be shared between the nodes. So you will have more memory in total than if you're working on a single machine.
Yes, so you have a way of communicating between the nodes. You have software that use the very fast interconnect and then can address memory directly on another node.
Yeah. Okay. And then, yes, so for shared file systems, typically you will have then some storage which is external to each of the compute nodes, but it is accessible to both the login node and to all the compute nodes. That means that if you have a file on the shared file system, you will be able to see it everywhere, which is very important for having an efficient way of working. So if you have your input data that you want to analyze, it doesn't matter where the job goes on which compute node, it will have access to those files.
And you experience this every time you log in because it's arbitrary which login node you end up on. And
yeah,
the login node wants your home area, so
exactly.
It doesn't matter.
So if I do pwd for print working directory, I will see that I am on my cluster/home/mic and pair, and you will see the same but with your username. And if I had gotten into login 4 instead, I would be exactly in the same place and I would see exactly the same files that I have on my home folder because it's shared on all the nodes. And the same is with typically this. It will be called different on the different systems you are, but I think in NRIS, all the project areas, folders for projects are in /cluster/projects. That's a typical name. So if I do that, I will see lots of projects. I don't have access to all those projects, but I know that I have access to the training project NN997K. So you could try that yourself with LS. And then I see that there are files there. So I can access those also. And if I was logging into a compute node, I would be able to see the same. Yes.
We have a question whether the Zoom recording will be shared or could be shared, and this will be on YouTube.
Yes.
Not immediately, but it will be published on YouTube.
Yes, so we do some editing and making sure that nothing is shown that should not be shown, and then we post it on YouTube after some time. So it will be available.
The channel is NRIS or?
Well, we can put that in the collaborative document, actually. There's actually videos from several from previous years, and there's other instructional videos also on the YouTube channel that could be useful for people to see.
There is already links in the collaborative document on top to the video archives.
There, yes.
Yeah.
We have some short instruction videos and we have training videos. I guess the training videos are from the NRIS training, these onboarding courses. There's a lot. Yes, so as I said, there's a difference between the local file system and the shared file system, and basically the point is that in the local file system, the one that was actually installed on one compute node, that's not accessible on another compute node. Typically, we call that scratch. So you will encounter that word scratch in the documentation, and it can be useful for you if you have files. You might want to place files there temporarily, for example, temporarily output files that are produced when you do your analysis. Maybe you have large amount of output files that you don't have place for anywhere else. In Scratch, there might be place, but it's temporary, so things are cleaned up there. So anything that you want to keep for later on, you have to move either to your well, typically the best place to move it is to the projects area in the end. But yeah, this is all details that you will get more acquainted with later. So I already showed you these commands. So please go ahead and write pwd for print working directory so that you can see what is the path to your home directory. And it should look basically the same as mine, unless you're on some other non-NRIS HPC cluster doing this test. And obviously, the username should be a different one than mine. You can also do, yeah?
The user area or home directory are becoming very tiny. It's becoming very small. I think on Olivia, it's just 10 gigabytes.
Right.
So the home area will be more for configuring your environment than for storing any type of data.
Yeah. And typically they are quite small, the home areas. So don't think that you can put lots of data there. The kind of storing larger files will be in the project areas, and that's where there is space for you. You can also do ls for list directory. You might have just an empty folder. I have some files there already, but ls just shows you basically what's in the folder right now. Good. So I think yeah, we can try an extension of the ls actually, because if you do ls-h with the option -h, that means all, it also shows you hidden files. And hidden files are files with this dot in front. So you see that I had many more files now. So these are the files if I do just ordinary ls, and with ls-h, you see lots more files. I have like .bash history, .bash profile, .bash rc, .cache, and .local. Some of these are probably, or I know some of these are because I have installed some software and they have some hidden folders with configuration and logging and so on in there. Others are probably something you will have, like bash rc. Yeah.
I often use ls-art.
ART?
Yeah, then I get an L as well, the long. Then I get the last modifier file in that directory.
So let's see, L is for, we should open the manual now, but L is for
the long listing.
Long listing, exactly. Then you have all this information,
yeah.
Which tells you about what's it called? The permissions, ownership. There's information about when the file was edited and the name. And then R is reverse, and T.
Yeah, I don't forget. I've forgotten what T is.
I often do ls-lhrt. Yeah, that's kind of what I often use without the A. Yeah.
Yeah.
Yes. Let's see. There's one thing that I want to see if I have. I want to see if we have the cheat sheet also here, or if we have it only on the. No. In yesterday's class, in the material for yesterday's class, there is a cheat sheet of Linux commands that we use in the course, and we can link to that in the collaborative document so that you can have a short kind of list of the typical commands that we will be using. Yes, I think that's mainly it. Is there something I forgot to say? Or are there some questions?
There are some questions here which we can discuss, perhaps.
Let me see.
So there is this scratch variable which points to the scratch or work. Or no, maybe be careful. Work and scratch, is that the same? No. That's
We
not
should
the
check
same.
documentation.
Yeah. So there is the scratch variable that points to the scratch or temporary storage area. So you don't have to remember where it is for the different systems.
So this here, so we can explain that what is a variable. So in this, in Bash, that is typically the scripting language that is like the most common and what we use here in this course. You can, so we can assign variables and we can call variables like this. Let's say if I want to create a variable hello, which says hi there. Okay, looks like I've done nothing, but then I can look at the variable by writing echo and then the $sign and then hello. And then you will see that it outputs actually the content of that variable. So dollar, and then we typically use opposite of lowercase, uppercase words for indicating these variables. At least these ones, home and user and some special ones. Yes, and I think the scratch variable is active. So as you saw, if I do echo scratch, there's nothing there. It just there's an empty output. And I think it gets set in the Slurm setup. I don't quite remember how that works. But
I can comment on this, Maiken, if you like. The scratch variable is set by when the job starts. Slurm sets it to a temporary directory which only lives as long as the job runs. When the job finishes, that directory is deleted, and it contains the job name and so on, so you can find it. But when the job terminates, everything in that directory is deleted, so you don't really have to clean up. Slurm cleans up for you.
Yeah. So it's a great place to have like temporary files that are kind of created while you're running, but you have to have a system that it gets copied over to a place where you will have access to it after the job is run. And we have documentation on all of how to do all those things. Yes.